few screens a year. And every time we somehow find similar problems, and I want to somehow introduce those problems to you and how we try to deal with them, what kind of solutions we're developing at the moment. Just a short outline. What is Scopem? Where I'm exactly from. There's still something in Scopem that I'm in. What is big data for us in Scopem and the high content screening bottlenecks that we find. And I will present you the 3 problems and how we try to attack them together with our partners. So quite a lot of work is that we develop with companies or with partners. So I hope that you can get something useful out of that. Maybe you will use some solutions in the future. So Scopem is a big facility. We have 50 various devices. We are about 30 people, and we have 700 users at the moment active. And there are devices that are very data intensive. So I will talk about screening. It's a screening microscope, but we also have cryos, almost 2 of them. One is being acquired now. It will be soon available. And within Scopem, there is the image analysis unit. That's we. This is Simon. Simon is my boss. That's me. And Shimon and Javier, the computer scientists. Simon is a physicist. I'm a bioinformatician. So what we do in Scopem, we mostly help the users, so user group, to analyze images and process the numerical data out of images. And for us, at the moment, the biggest flow is high content screening. But we also do, we are more and more involved in processing cryo-EM data. And Shimon is also involved in digital pathology, which is also a big data subject. So about the high content screening, as I said, we have quite a few screens where we are involved. This can range from 6, 10. We are not fully involved in all of them, but in many we are from the beginning till the end. How it starts, the user comes and has some problem with some cellular mechanism, and he would like to use a brute force approach, which is a screen. And then we help him to do that. So we are often, as I said, we are often from the beginning till the end. And why we think this is big data? There are problems that are much more data intensive in petabytes, not terabytes. But for us, it's about how many images we have, how many cells are in the typical screens, and how many features, like on this picture that is from a recent screen that we work on together with Vidya. You can actually see cells, segmented cells, and this foci of LDL, and there are billions of them in this kind of screen. So this is for us a big data to capture that and analyze. So this is a workflow for the ones that don't know much about screening. And I just put the marks of what is a long process, what is short, and what doesn't take so much time but can be also long. So usually it starts with preparation, and this can take, overall, it takes about a year, as far as I know from my experience. This preparation is long process, then experiments are not so long. Imaging is short, and here where we come, what we would like to have immediately after imaging, we would like to take a look on the data, and we would like to do it mostly for the quality checks, and we would like to have something that we can immediately display data and do it in a large scale. So something like Urs explained, and he actually, the solution that and the problem that we have is very similar, and the solution that we developed is also very similar to what he showed. The second step is image analysis. We use for that a cell profiler, but we often are stuck there, and we use a lot of time to go through the image analysis, because segmentation occurs, so finding cells and finding this foci occurs problematic, and we cannot process everything as fast as we would like to. We spend months on improving this part. And then there's a data analysis where we are involved in validation, and this is not the thing that we do for the users, but between image analysis and data analysis, the data is usually often straightforward. There's not nothing too complicated, but we are missing this connection where we can go from data to images. And this is a third problem and solution that I will just discuss in the next slides. So how we do it now, how we were doing it for several years, we were using OpenBees. And OpenBees is okay, I guess many of you know it. You can load images, we have pipelines to do it automatically. We can go through the screen, we can also upload the overlays. But it's not so nice if you want to go fast through images. So you cannot, it takes usually long and it's not so handy. So for doing this again and again and again, we found it a bit slow solution. And the second thing about OpenBees is that you cannot really connect it to the analysis which we were doing so far with R or Python. So one is okay, the other is also okay, but they are not connected. So the solution to problem one, it's exactly like Urs showed. He actually has stolen the show, so I will not show you any movie anymore because it's more or less the same. What we want to do, we have a working prototype that we are developing with Mario Amenauer, where you have a Google Map-like tool that you can screen through the whole experiment, so all the places that you have up to a single cell, and you can take a look fast on how many cells you have, if they are in good condition, if the zoom is okay, and so on and so on. But we don't want to do it. This tool we only want to use for inspection, so we don't want to develop anything big. It should be small and fast, and that was the idea behind that. And the solution is already working. It should be deployed till the end of the year. Also for the users that we have. The second problem, as I mentioned, so these are two images from a recent screen where we only have to find nuclei. And as you can see, this image on the left, this was used from the preparation stage. So we already, what you also see over here on those cells is that these lines that show that we can actually find cells with a cell profiler, so we can segment the image. And we are finding all the cells over here. So we have nice segmentation. We can find and count all the cells in that given well, or on that given image. But now when we have all the data, so our 100 plates, we find that in quite high percentage of the images, they are so different that what actually happens that with the same parameters that we tuned before, we miss a lot. So we don't find cells because they are too big or they cluster a bit. And the whole parameterization procedure has to be performed again. And what is more problematic is that we have to find some common parameters, and often this is not possible. And we have to go to decide when it's good enough. So what we do at the moment, what is the again solution that we developed and that we have a prototype already working, is that we have a script that is implemented in Fiji, that we click on those cells, and then we tune with machine learning the cell profile parameters such that we find the same cells that we clicked with within our clickable tool, and then we optimize parameters until we find all the same cells and in the same areas. So that's one part that we hopefully will be able to use on more cases. And the second thing that we are also working now, and I hope this will go in a good direction, is that for this kind of problems, it seems that, and other people also work on that, that for example for nuclei you can train the neural network and you can actually have just one network that will be useful for many different screens, so you will not have to do any kind of machine learning on your given experiment. And this is ongoing work with me and Simon. So problem number 3, as I mentioned, we had a solution for data analysis. We also had a solution for showing images, but we could. It was annoying that we cannot see, for example, where the given well is on our scatter plot. So we cannot. We have a scatter plot, but we don't know to which images this corresponds. But not only well, it could correspond to a cell, or it could correspond to a plate. So we scatter something, and we would like to immediately go through it and find the corresponding images. And we went through what is there, and actually gene data, I know there are quite a few people from gene data here, they have a nice solution. So we tested that, and it works very nice, but for us, unfortunately, it was too expensive, so we couldn't afford, we didn't have so much money to buy it for a long period, because that was also important. And what is also very important for us is that it's not only for us, but also for the users. And since we have quite a few users, we have to have quite a few copies of licenses, and that was a limiting factor. Of course, you can build something yourself. That, for me, for example, that wouldn't be too difficult to work in a Jupyter notebook and then use some libraries like Bokeh that you can immediately display images and scatter plots. So, but for most of the people that I work with, that's too complicated. They will not be able to do that. So, like a year ago, a year and a half, actually Simon met a person from Janssen Pharmaceuticals, and they were having this program that was developed for them by Open Analytics, software house, and he was really happy with this. And at that time, they actually decided to put it open. So this was not anymore just for Janssen, but other people could use it. And I think, and it's not as good as gene data, but it has a lot of features. So the most important feature for us, this connection of data to the images, was there. And what was also important is that it had a server-client architecture, so we could deploy it on user computers. So I will just show you one screen that you have a general idea how it looks like, but you can go on the web page and see. What you see over here is a screen, the same that I showed you before, so the same data. It's a well. There are many wells from that given plate. And here, these are cells that correspond to that well. And what I scatter plot over here is some kind of features. So features are again here for a given cell that are associated to those cells. And what I do on the scatter plot, I do selection here. And these cells get immediately selected, so you don't see any more other cells. You can color them, or you can remove the cells that are not selected. So now I display just those cells, and those cells, you don't see that, but it's because it's in red, they also get selected here. So you see the cells here, you see them here, and you can also take a look on image, and you see where they are located. And what is nice about that is that you can do it on many levels. So you can do the same. You can display many wells, like here, and you can do a scatter plot on well features, so some kind of features. And then you can also go through that and compare it to scatter plot. So that was actually the thing that we were looking for. And we had some money to use it. Still, it was not really good enough for us, So we decided to spend money to actually develop it further. And at the moment, we have a long-term agreement with this Open Analytics. And they are developing the parts that we're missing and that we would like to have. So, for example, the Mac client or Python scripting. So you can. So here you don't have to plot anything that they implemented in the open in these menus, but you can actually have a Python shell and you can do whatever you want with the data, and then you can see the plot and you can also see the corresponding image. And so on and so on. So there are quite a lot of features that they are implementing at the moment. And the idea is that most of them will be also available for you. So hopefully it will be somehow useful. So 3 things. Quick visualization. It seems like there's quite a lot of people looking at it, and this is a missing feature. Segmentation. I guess there's also a lot of people that would like to improve that, to not lose too much time on that. And this connection, which I don't think there are many ready solutions now. So just acknowledgements. So this development that we do with partners, or they do for us, we have a grant for that. So we spend money from ETH Scientific Equipment Fund. Most of the screen is actually managed by Roger, who is directly talking and finding customers. Mario is developing the image viewer, and Friedrich is the Phaedra developer. That's it.
So at which point do you feed data to Phaedra? Does it take in output from cell profiler, or?
So it also have this automatic data capture modules, so you can take it from the microscope as soon as it's there, and then when you have another part, you can feed it in when it comes.
But this has to be segmented already data, right? Or?
No, it can be just raw images, and then when you have a segmentation, then you can upload it